So hi everyone. Today we have Anna. I guess I forgot to say how to say your last name. Is it Weigandt?
Weigandt. Yeah, it's
Weigandt. Okay,
German.
that works. Okay, so today we have Anna Weigandt from the University of Michigan, who will talk about the Castelnuovo-Mumford regularity of matrix Schubert varieties.
All right, so thank you so much for having me here. So yeah, I'm going to talk about work that kind of is in a few different projects of mine. So kind of the first bit of the talk is joint work with Jenna Ratchcock, Yi Ren, who was an undergraduate at the time, Colleen Robichaud, Avery Saint-Dizier. And so this paper is very shortly appearing in Proceedings. And then also work, which you can't find on the internet yet, but will hopefully be there soon, but work in progress with Oliver Pechenik, who's here maybe to help me field the chat, and David Spire. So yeah, let me tell you a bit about this. And I'm gonna start with the sort of commutative algebraic motivation for this problem. So I'm not gonna go like very formally into the weeds of like the definitions and where things hold, but I'm gonna give you kind of an idea of what this Castelnuovo-Mumford regularity is. So we start with a finitely generated graded module over some polynomial ring and take a minimal graded free resolution. So you have just different copies of your ring R, and you might have to do some degree shifting around. And so what you're going to do is try to get some measure of how complicated this free resolution is. And so you are thinking about sort of degree shifts that are happening. And this BI is going to be the maximum of these beta J's, or of the J degrees, so that beta J is not equal to 0 in this direct sum decomposition. So then the regularity of your module is going to be the minimum integer R, so that R plus I is going to be greater than or equal to BI for all I. Now this is too vague, so let's dig in and like point at things in an actual example. Okay, so here we have a polynomial ring. Oh, I should check. Can you see my mouse when I wave my mouse around? Good. Okay. So here we have a polynomial ring in two variables, and we have an ideal that's generated by x to the fifth, y squared, x squared, y. And so you can start to think about how you might resolve this R mod I. And so you want to make sure that your image is going to be your kernel at each step, and we're taking a free resolution. So we're going to have just a bunch of different copies of R that are going to be direct summed with each other. But then this graded resolution means we want to formally make sure that when we map things from one place to the next, the degree stays the same. And so you do kind of this trick where you say, well, maybe the constants in this R of -5 just formally have degree 5, and the single variables have degree 6, and so on. And so that makes these sort of linear maps by, say, matrix multiplication just preserving degree. And so this is some sort of formalism. And if you're not really happy with resolutions, you can just kind of look at the picture. But the idea is now we start looking for the maximums of these different degree shifts that occur in each of these steps along our resolution. So this B0 is just going to be 0. This B1 is going to be this -5, or sorry, 5. B2 is going to be 6 over here. And so then the regularity of R mod I, we can see that if we set R equal to 4, then that means that R plus I is going to be greater than or equal to BI for all I. And so again, like if you're not happy with like the resolution itself, just keep in mind that it's some rough estimate of how difficult, how complicated this resolution can be if you take a minimal free resolution. And it doesn't depend on your choice of minimal free resolution, it's an invariant. Okay. And so if you don't want to take resolutions, when you have nice enough modules, you can use another tool from commutative algebra called the Hilbert series. And so if you have a graded module over your polynomial ring, the Hilbert series is going to pick off the degrees of these the dimensions of these different graded pieces thinking about them as a vector space over your ground field. And so here we set up this just formal power series where the coefficient of t to the I is going to be the dimension of the ith graded piece of your module. And then when you're in nice enough situations, you can always write your Hilbert series as this ratio where in the denominator you have a 1 minus t to the n, where n is just the number of variables in your ring. And the numerator, it's not some formal power series, it's just like a polynomial. So it's instead of thinking about this infinite series, it's just a little bit nicer, more compact information, just repackaging sort of this dimension information. So again, let's take a look at just a concrete example, returning to our ideal from before. When you think about R mod I, you want to think about the monomials that don't get killed off when you take this quotient. So for instance, 1's still fine, x is good, all the way up to x to the 4th, but x to the 5th gets killed off when we quotient out by I. And then we can have y, we can have x times y, but this x squared y is going to kill off anything beyond here. And then when we start getting powers of y squared, those vanish. So here we have just really a finite quotient as a k-vector space. So we can just start counting how many generators for these different graded pieces we see. So there's one thing in degree 0, there's two things in degree 2, two in degree 1, 2 in degree 2, 1 in degree 3, and 1 in degree 4. And then we can repackage this Hilbert series, so we see our k polynomial here. So this is just a way of, again, getting at the information about the different graded pieces of our module. Okay. And there's a really handy lemma when your ring is nice enough, when it's something called Cohen-Macaulay, meaning its depth is equal to its curl dimension, then the regularity can be expressed as just the difference between the degree of the k polynomial and the height of your ideal. Or if you like thinking about like varieties instead, you can think about like the codimension of the vanishing of R mod I. And so using this lemma, we can just kind of skip knowing about the free resolution and talk about the k polynomial instead when you have a Cohen-Macaulay ring. And so we can compute, for instance, we already saw this k polynomial. You could check that the height of this ideal is 2. And so this is going to tell us that the regularity is 6 minus 2, which gives 4. So again, free resolutions, they can get messy, they can get big. And if you just happen to know the k polynomial already, then you can get an idea of how complicated these resolutions can be. Okay, so the ideals that are going to be of particular interest to us today are Schubert determinantal ideals. So I'm going to start with something a little bit more classical. So you can take the space of, and you get some polynomial by putting all those variables into your ring. And a determinant is just the ideal that's generated by size k minors in this big. And so, for instance, we could take the 2 by 2 minors in this 2 by 3 matrix, and we can find 3 different 2 by 2 minors in here. And so if you think about like the vanishing set of this ideal, say the vanishing set of k plus 1 size minors in one of these generic matrices of generic variables, what you get as a subset of the space of n by n matrices is going to be matrices whose rank is at most k. And so this is just a very classical sort of ideal and a classical sort of geometric thing to study. And so matrix Schubert varieties, they're just defined by a whole bunch more determinantal conditions. So now you can have determinants of varying size. I'm not going to really get into the weeds of this definition, but you should know that this sort of presentation of the ideal, it actually has way more conditions than you need. And so you can write them down with fewer minors, but still potentially a lot of minors. But here's just an example, the ideal for 2, 1, 4, 3, say in a 4 by 4 matrix space. It's just generated by this single variable and this 3x3 minor. But these things can get a lot more complicated, but morally they're generalizing these determinantal ideals. Okay, so these Schubert determinantal ideals, they have a lot of nice properties. They're radical, they're vanishing set, it's irreducible. It's actually, well, the radical condition means that if you're thinking in terms of like scheme theoretic structure, it's just reduced as a scheme. The height of the ideal is something, it's the Coxeter length of the permutation, which I'll talk more about later. Happens to be a Cohen-Macaulay ring. Lemma that I know applies. And then just generally Schubert determinantal ideals, they generalize a lot of nice families of ideals that you see in the commutative algebra literature, like determinantal ideals or ladder determinantal ideals. So varieties of complexes in some sense fall inside of maybe a more general setup with analogs of these sort of matrix or Schubert determinantal ideals. So there's just a lot of these kind of you might study. With this, I'm going to take maybe a sudden change of pace and talk about Grothendieck polynomials, and then I'll go kind of back to the commutative algebra before we hit our 5-minute break. Okay, so Grothendieck polynomials, they were introduced by Lascaux and Schutz and Berger to study the K-theory of the complete flag variety. And so they're indexed by permutations, and they have this recursive definition where you say that the Grothendieck polynomial for the longest permutation, which in one line notation is n minus 1 all the way down to 1, this is just a single monomial of this form. And you get the rest by applying this sort of operator. So a kind of divided difference sort of operator. And so I'm going to just show you, rather than reflecting on this formula too long, just what the Grothendieck polynomials for S3 look like. So we start with this monomial up here. You'll notice most of them are actually just monomials. That's a feature of this being a rather small symmetric group. But this one's kind of interesting here, this Grothendieck polynomial for 1 through 2. It's inhomogeneous. Its coefficients, they alternate in sign with degree. So Grothendieck polynomials have a lot of these nice sort of properties. Their coefficients in particular are integer coefficients. And whenever you have integer coefficients floating around, you hope for some combinatorics, and there's a lot of nice combinatorics. So for instance, you can write down Grothendieck polynomials as a sum over these objects called pipe dreams. So Nantel, in his work with Sarah Billy, he did sort of the cohomological version of this. So these pipe dreams that you see along the top row, to write down a Schubert polynomial, if those words are things that make you happy. And then the sort of K-theoretic nature of these Grothendieck polynomials means that you have some higher degree terms given by these non-reduced pipe dreams. So I'm not going to get into the weeds of how exactly you write down the pipe dreams, but you might notice that the way you get a monomial off of a pipe dream is you count how many crossings there are in each row, and that gives you the exponent of the variable corresponding to that row. So for instance, we could look at this pipe dream down here, in row 2 in column 1, and it has 1 crossing in the first row, 2 crossings in the second row, and 1 in the third row. And so that gives us this x1, x2 squared, x3. So again, I'm not really telling you how to define these things, how to write them down, but I just wanted to show you a picture so that you see that there's some nice combinatorics that you can use if you would rather not think about these divided difference operators. Okay, so why did I bring Grothendieck polynomials into the picture? Well, Knudsen and Miller, they showed that the K polynomial of R mod the Schubert determinantal ideal is just a substitution of into this, a specialization of this Grothendieck polynomial. And so you can take each of the x variables that are floating around and plug in a 1 minus t and this gives you your K polynomial. And so then, well, we had by Fulton that R mod IW was Cohen-Macaulay. And so this really tells us, based off of this lemma, that if we want to know the regularity of the R mod, the Schubert determinantal ideal, it's just the degree of the Grothendieck polynomial minus the Coxeter length of the permutation, which is again telling you this height of the Schubert determinantal ideal. So we can kind of at this point start to set aside all of the commutative algebra entirely and just really focus in on asking what is the degree of a Grothendieck polynomial. So the upshot is the degree tells you this regularity. So there's certainly some non-explicit formulas floating around. Like you could say, well, the degree is the maximum number of crossings that you can find in a pipe dream for W. But it gets kind of hairy to start writing down all these pipe dreams and start sorting through, and there can be a lot of them, and it's just not very explicit. There's also a theorem of Leonard, which tells you how to expand a Grothendieck polynomial into Schubert polynomials. But these coefficients, they're given by certain 0-1 arrays that to me feel kind of very much like pipe dreams still. So it's just sort of trading difficulty in a certain way. So yeah, the motivating problem for the work that follows is to find a simple and explicit formula for the degree of the Grothendieck polynomial. So remember before, we realized that if we just know the degree of a Grothendieck polynomial, that tells us the regularity of the corresponding Schubert determinantal ideal. And so what I'm going to start with is kind of as a warm-up, I'm going to give you one formula for the degree of a Grothendieck polynomial in the case of symmetric Grothendieck polynomials. So this is the work with the whole zoo of authors, Jen Ratchcock, Yi Ren, Colleen Robichaud, Avery St. Dizier. So yeah, I'll start. Well, in this crowd, you know what a partition is, but a partition is a weakly decreasing sequence of non-negative integers. For this formula, I really do want to keep track of 0 parts. So for me, it's important that this partition has these 5 different parts. But when I draw, say, its corresponding Young diagram, I don't see that 0 part in my picture, but that's okay. So that's a partition. And then there's special partitions that are called staircase shapes. And so these are just partitions of the form k, k-1, and so on down to 1. And so this delta k is the staircase of size k. And then the Sylvester triangle of a partition is the largest staircase shape that fits inside of your partition. And by fits inside, maybe I'm conflating partitions with their corresponding Young diagrams. And so you want the staircase Young diagram to fit inside of the Young diagram for lambda. And then SV of lambda is going to be the maximum side length of this Sylvester, or of the staircases that fit inside of your partition. So the side length of your Sylvester triangle. So for instance, in this partition 63110, the Sylvester triangle that fits inside has side length 3. And so this SV of lambda would be 3 in this case. And then I'm also going to introduce notation, this mu I. Maybe it should really be a mu I of lambda, but that's just too much notation. So mu I is going to be the partition obtained from lambda by throwing away the first I columns of the Young diagram. And so lambda, if it's this 63110, this mu2 is going to be this partition here, this 4-1 that you get by throwing away the first 2 columns of the Young diagram. And so with that, we have a very, I'd say, simple explicit formula. Maybe, we'll unpack it. But the degree of the symmetric Grothendieck polynomial that's indexed by lambda is going to be the size of lambda, so the number of boxes in its Young diagram, plus the sum over the parts of lambda, where you just take the this SV of mu lambda I for each I. So here, for instance, if lambda is again 63110, we can write down lambda 0 or mu 0, where we threw away no columns. So that's just lambda. So this has 3, and then this, we have a staircase of size 2 when we throw away the first column. And then we have, when we throw away the first 3 columns, because we have this part 3, we get a 1. We could throw away all the columns and we get an empty partition. No Sylvester triangle fits in the empty partition. And so then we just start adding up over these parts. And so we get 11 because that's how many boxes there are. And then plus 0 for this 6 part, plus a 1 for this 3, plus a 2 twice for this 1 part. And then this 0 part gives us this 3. And so we add them all up together, and then the degree of this Grothendieck polynomial is 19. So I've not actually written out the Grothendieck polynomial for you, nor have I told you how to translate this partition notation to get to a permutation, but you always can. This is going to be a Grothendieck polynomial for some permutation and some large enough symmetric group. So this is a special case of the more general problem. Okay, so are there any questions about this formula? All right, so that's again what I had done previously, and then we're also extending this. So in work with Ratchcock and Robichaud, we have similar formulas for vexillary permutations, so those which avoid the permutation 2, 1, 4, 3, and permutations which avoid the pattern 1, 4, 3, 2. And then we also use the vexillary formula to give regularity formulas for certain Castelnuovo-Mumford varieties for their coordinate rings. So I'm not really going to talk more about these directions, but there's similar style sorts of formulas in these cases. So what I'm going to focus on for today is joint work with Oliver and with David Spire. And so I'm going to start by just discussing some codes and statistics on permutations. So I'm going to start with one that's very familiar, likely, and then one that I'm imagining is new. Okay, so the very familiar one is the Lemur Code. So the Lemur Code, it encodes inversions of the permutation in a certain way. And so this Li is going to be the number of things following the jth position which have smaller values than, Li, sorry, I'm mixing up my i's and j's. So it's going to be the positions that are further out than I that have smaller values than W of I. And then we can just sum up all these different LIs to get the Coxeter length of the permutation. This is the number of inversions. It goes by a lot of different, has a lot of different properties. But one thing that this does is the Coxeter length of W tells you the minimal degree of the monomials in your Grothendieck polynomial. Now, that wasn't the statistic we were looking for necessarily, but that's something that it does. So let's just look at an example. So over here, I've started to write out this permutation W, and then at each step, I just kind of drop off another entry from the front. And then I've circled the things that are in inversion with the different starting values of each row. So for instance, with this row 3, 6, we have 4 and 5 and 2 and 3 are all smaller than 6, so those get circled. If you're like me and you like Ratha diagrams of permutations, this inv code, the Lemur code, is just recording the number of boxes in each row of the Ratha diagram. And then you get to just like add up all these boxes or add up all these circles to get the Coxeter length of your permutation. So again, this was meant to be perhaps a familiar statistic on permutations, and I'm going to move to the new one next, which is the Ratchcock Code, named for Jenna Ratchcock because she got us on this kick of thinking about degrees. So the Ratchcock Code, here again, this is going to look like maybe too many indices, and I'll flip to an example momentarily. But Ri counts the size of the complement of a maximal length increasing subsequence in Wi, Wi plus 1 up to Wn, which uses Wi as part of the subsequence. So it has to start from Wi, and then B, a maximal length increasing subsequence subject to that starting with WI. And then this statistic Raj is just the sum of the different pieces of the Ratchcock code. So again, same permutation as before, and I've written down a similar triangular sort of array, but now what I've boxed in this array is a maximal length increasing subsequence. This example is maybe a little too rigid because there's a unique maximal length increasing subsequence for each row. That doesn't have to be the case, but let's just look at, for instance, row 2. So we could start with 1, and then like we could try picking 6, but then the best we could do was go to 8. So that would just be length 3. So the one that actually works is 1, 4, 5, 8. And then we take its complement and we get a 3 here. Okay, so this again is the new sort of code. Are we feeling sufficiently happy? Okay. And then Raj is what happens when we sum up all these different things that didn't get boxed up in this picture. Okay. So yeah, there's a nice relation between this Raj code and the env code. Entry-wise, the Raj code is greater than or equal to the env code. And you can see this pretty quickly by noticing, well, if something's in inversion with the starting thing, it can't be part of an increasing subsequence starting from that. So this is just a quick, easy lemma from the definition. So here I've circled the things that are in inversion with the first thing in each row. And then the boxed things are that same increasing subsequence. Okay, so I'm going to introduce just another thing that has to do with this Raj statistic. So there's a way that we can kind of repackage it if we don't care about the Raj code. We can draw what we're calling a blob diagram because it kind of looks like a bunch of blobs. So what you do is you look at, this is the graph of the permutation. So I've put dots in position I, WI for each I. So for instance, since in this first position is a 7, in the first row, we put a dot in column 7. And then what you do is you look for the dots that have nothing south or east of them, no dots south or east of them. And so here, like, we can just sort of circle the ones that have nothing south or east of them, and then we ignore those dots. And then we do this again. So we look for dots which have nothing uncircled that says south or east. So this is where things, all of those. We could circle this dot next, and then this dot next. That's the blob diagram associated to this permutation. And so the blob diagram, it gives rise to a composition that we call the shape of the permutation. And so we just kind of read the blobs in order, or like maybe reverse order of where we circled them. And so we get a 2 in the last position because there's 2 circled dots. We get a 4 in the second to last position because there's 4 circled dots, and then 1 and 1. And so every permutation has an associated composition in this way. And Raj only depends on the shape of the permutation. And there's a very explicit sort of formula where the thing to be a little careful about is we index so that if W is in Sn, piece of alpha. But anyway, the exact formula that Raj only depends on the shape. So here, for instance, as a sanity check to make sure that I can add correctly, we can compute Raj in this sort of way, and we would get 19 again. Okay, so why did I introduce all these this new random statistic? Well, it turns out this new random statistic is the right statistic. So the theorem in forthcoming work is that the degree of the growth and peak polynomial is Raj of W. So yeah, what I'm going to do in the remainder of the talk is give you sort of a sketch of the proof that goes into this. But first, let's just look at kind of an example. Here is our sort of running example permutation W, and I've drawn a pipe dream for W that has the maximum number of crossings. And so if you're a person who likes to think about pipe dreams, I would challenge you, like you could try to find one with more than 19 crossings, but you won't. So this is a maximal pipe dream that's giving you something in the top degree of this growth-unique polynomial. And notice even better is that the number of crossings in each row corresponds to this Ratchcock code from before. So I'm not going to dive too deeply into what's going on there, but just sort of the Ratchcock code of a permutation is telling you a specific monomial in the top degree part of your growth-unique polynomial, and it's sort of a Lex last sort of monomial. So we can get even more specific, but I'm gonna mainly focus on Ratchcock going forward. Okay, so what we do is we start by thinking about kind of easy cases of permutations. So one of the easiest sorts of permutations that you can have is a dominant permutation. In other words, it avoids the pattern 1, 3, 2. So when you have a dominant permutation, the inv code is equal to the Ratchcock code. And in particular, the Coxeter length of the permutation is equal to Ratch of W, because each of these codes you're summing up, they're different things and they're the same codes. So now I've drawn W is a dominant permutation. And so you can sort of imagine that if you're looking at this thing, the 1, 3, 2 avoiding condition is meaning that these maximal increasing subsequences, anything that's not in them has to be strictly less than the starting thing in this row. Otherwise, we would kind of force a 1, 3, 2 pattern. And so everything that's in the complement of the unique maximal increasing subsequence is just going to be an inversion. So this, again, Ratchcock code really is equal to the inv code when you have a dominant permutation. And also, dominant permutations have really easy growth-unique polynomials. It's well known that the growth-unique polynomial for a dominant permutation is just this monomial, which is x. Maybe this should be a bold x raised to inv code, which happens to be Ratchcock code. So here I've written for this dominant permutation, just this monomial. You can even, again, if you're a person who likes Rotha diagrams, you can just write down the Rotha diagram and count the boxes in each row. You could put crossings in the Rotha diagram and fill it in with elbows, and this actually gives you the unique pipe dream. So dominant permutations, really easy, really well understood. Okay, so the next class of what I would argue is easy permutations for us to understand this theorem with is this thing called layered permutations. And so W naught sup J, this is going to be the longest permutation in the symmetric group Sj. So it's reversing again the sequence J, J minus 1, and so on down to 1. And if you have a composition, you can form a permutation by doing this kind of cross operation with permutations, which is really just kind of stacking permutations together blockwise. And so it's probably best to just look at this picture. So if alpha is the composition 1, 1, 4, 2, then we're stacking together blocks. So here's a W naught 1, a W naught 1, W naught 4, and W naught 2. And so you just stack these blocks together to form one big permutation. So that's a layered permutation is a permutation that's built in this sort of way. And another lemma is that layered permutations, they have a unique top degree pipe dream, and it has Raj many crossings. And so since it has a unique top degree pipe dream and you can count the number of crossings in this pipe dream, you can just count explicitly that this is going to be equal to Raj of E alpha. And so for me, it's almost easy to count elbows instead of crossings because you can kind of notice along diagonals, kind of at the end of each block row, you're going to get a diagonal that has just elbows. And so you can just kind of subtract off some elbows and do some reformulation into that shape-based formula that we had before. So I'm not going to get into the weeds of all that indexing, but it's an easy translation because we're able to know this top pipe dream so explicitly in this case. Okay, And then the kind of last tool that we need to think about why this theorem might be true is the two-sided weak order. And so we have kind of this left weak order on the symmetric group, which is defined by covers of the form SIW is left less than W. So this SI is the simple transposition exchanging I and I plus 1. And there's a right weak order where we just act on the right instead. And then the two-sided weak order, we take both of these types of covering relations and take the closure of the order that this gives us. So I'm just doing in this slide for S3, kind of you can compare and contrast the left order on S3 with the right order on S3. Somehow a lot of this project wound up being us keeping track mentally of whether we were using the left order or the right order. So some handy things, the left order in one line notation, it exchanges the value I with the value I plus 1. It swaps where they appear in the string. The right order exchanges adjacent positions. If you like thinking in permutation matrices, the left order is column swaps, which might be opposite from what you would hope it would be, but that's right. And the right order is doing adjacent row swaps. Anyways, then you can take the sort of transitive closure of these orders to get the two-sided weak order. For S3, maybe it's not big enough to get a feel for how this is different from, say, strong group order, because it's not, but in higher symmetric groups, you start to see differences between these both sets. Okay. And so now that we have some idea of what this left-right order is, we can appeal to this lemma. So if you fix W in Sn that has shape alpha, there's kind of two facts, which is one, W is greater than the corresponding E alpha in this left-right order. And two, we can find some dominant permutation that has the same shape as W and is greater than W in this left-right order. So here, W is kind of our running example. Here's its corresponding E alpha. And you could check by doing adjacent row and column swaps that you could get from W up to U. So we have kind of this almost W is sort of sandwiched in this poset, but maybe you have to climb up a bit in one of these left-right chains. And then more facts. The degree of a Grothendieck polynomial is the same as the degree of the Grothendieck polynomial for its inverse. And if V is less than W, say less than or equal to W in this left-right order, then the degree of the Grothendieck polynomial for V is less than or equal to the degree of the Grothendieck polynomial for W. So one, if you like thinking about pipe dreams, fall pretty quickly from symmetry of pipe dreams, that between pipe dreams for W and W inverse, you kind of transpose pictures. And transposing it preserves the number of crossings. And then for two, you can think about this recursive definition with these divided difference sort of operators. And so what we're really doing is we're going down in right order. And as you apply this operator in the numerator, it possibly gets degree 1 higher, but it might have some cancellation in terms going away. And then we divide by a degree 1 thing. So the degree at best, it can stay the same, but it might start dropping as you work your way down this right order. And so by kind of transposing and taking inverses, we can work our way down in this left-right order. Okay. And then now we're ready for the proof of the main theorem. So we're going to stitch together, this talk has been a lot of lemmas, and we're going to kind of just stitch together the lemmas. So keeping the notation from before where U is a dominant permutation that's bigger than W, and E alpha is its corresponding layered permutation, what we get is dominant permutations, Raj equals the degree. Then we're climbing down in this left-right order, and so the degree is getting potentially smaller, but maybe staying the same. And then E alpha is a layered permutation, so this degree matches this Raj, but they all, by construction, have the same shape. And so they all have the same Raj. And so kind of by like just squeezing with inequalities, degree of W has to also be Raj of W. And so that's kind of the outline of how this goes. And yeah, that's all I wanted to say. So any questions?
Nice. Let's thank the speaker.
Wow.
Are there any questions? Mike.
So where does this statistic come from? Because you seem to have given it as a like, oh, here it is, and this is right. Was that known? Was that conjectured, or did you have to discover it?
Yeah, so I'd say maybe the fairest answer is it comes from David's sort of a convoluted way at this whole theory, and there's a lot of really interesting like left-right order combinatorics I haven't even dived into. But yeah, we actually started by sort of taking derivatives of Grothendieck polynomials and realizing that could tell us something about the degree. And by the time we got a handle and like all these weird statistics started just kind of popping out from this discussion. So that's not really the best motivation for where it came from, but it works. Yeah.
Yeah. Does it have Jenna's approval for the name?
Yeah, so we told Jenna we're stealing her name, and so she is at least resigned to it. Yeah, she hasn't stopped talking to me, which is good. Oh. Yeah.
Are there any other questions?
Does the analog of the Eulerian polynomial for the statistics factor well?
I don't know. Oliver is making a thinking face.
Yeah, I don't think we ever did that.
Because it seems like within a left-right, you just show that within left-right, the statistics stay the same, like and I think that you can pave the whole symmetric group by carpet like this. And so there should be some kind of nice distribution of the statistics over the symmetric group. That's my quick understanding of what's going on.
Yeah.
Are there other questions? Okay. Seeing none, let's thank the speakers again.
Yay.